All right, you guys, and now for number 5, we need to find the range, okay, the range of possible values of k such that this has at least one real solution. So I know that for a fact, a lot of you look at this and you say, all right, next question. But there is one big hint here that once you start noticing is going to help you to answer all exercises similar to this one. And it has to do with the last couple buzzwords, which say that this thing has at least one real solution. And so, of our tools that have to do with amount of solutions, there is only one. And your tool, which is in your formula booklet, by the way, is what we call the discriminant. And so the discriminant of a quadratic equation is this guy here. And so notice, where does the discriminant comes from? The discriminant, which is right there, comes from this right here. And so how do you interpret the discriminant? Anytime your discriminant is, for example, greater than 0, you have two solutions in your quadratic. If your discriminant is equal to 0, you have one solution. And if your discriminant is negative or below 0, then you have 0 solutions. Now, something I need to put a quick like disclaimer here is that it's two real solutions. It's one real solution and it's 0 real solutions. Technically, you can have imaginary solutions, okay? And this has to do with imaginary numbers. I'm not going to get into that, but basically, whenever you have a square root that is, for example, negative, you can solve it because I, your imaginary number, equals square roots of -1. And so through this, you can actually solve square roots of -4. I'm not going to show you because it doesn't really matter for this, but that is why here it says one real solution, okay? It's not asking you to go into the realm of imaginary numbers and crazy stuff. It's just asking for you to find the discriminant when it is greater than or equal to 0. Why greater than or equal to 0? Well, we said that greater than 0 was for two solutions. We said that equal to 0 was for one solution. And so if it's at least 1, then it is either 0 or greater. So discriminant has to be greater than or equal to 0. So awesome. We just identified that we need to use the discriminant and that is the way to go, and you're going to find the discriminant when it's greater than or equal to 0. But you're probably looking at this and telling yourself, how the heck is this going to be a quadratic? This does not look like a quadratic. What is this guy on YouTube trying to tell me? And so generally, you shouldn't trust people online, but just for today, you can trust me, okay? And so from here, once you identify the thing of the discriminant and that you want to try to reach something that looks like this, because this is where the discriminant comes from, it comes from a quadratic, right? Once you identify that, try to reach that, okay? And so for using the discriminant, it's also important, notice here, that they equal it to 0. Whoops, it's not letting me highlight what I want. For the discriminant, you need to equal it to 0. Okay, once you equal it to 0, you can use this guy here, you can use this guy there. I mean, it's not that you need to equal it to 0, but for our intents and purposes, for reaching what I haven't read, let's try to do that. Leave 0 on one side, okay? And so notice, your quadratic, its first term has an x that is squared. Its second term does have an x, but it's only to the power of 1. And their last term does not have an x. So if I try to replicate that, I can do minus 3e to the power of x to both sides. I end up with e to the power of 2x minus 3e to the power of x plus ln k. And this, believe it or not, is a quadratic. Now, I really want to explain why. See? So notice, a quadratic, as I said, its first term has something squared for x. Here is your squared x, okay? The 2x on top. For bx, you only have x, like 1 times x, right? So it's legit. right? And this last one does not have an x, so that is your c, okay? All right, I know this might be a little bit hard to like visualize or imagine, so another way that I can help explain it to you is imagine you're substituting just for a second, I don't know, that big A equals e to the power of x, okay? So if big A equals e to the power of x, that means this first term ends up as a squared. Because if you square both sides here, you end up with a squared equals e to the power of 2x. Ah, okay. So that means this first term can be rewritten as a squared minus 3. Oh yeah, so a is e to the power of x minus 3a plus ln k. This looks more like a quadratic now, doesn't it? But really, it's the same as this. All I did was replace big A for e to the power of x to make it easier to visualize it. Okay, but really, this is still a quadratic. So guys, I think the hardest part of this exercise is what I just explained, is realizing that when they say one real solution, you gotta be thinking immediately in terms of discriminant. And if you're thinking in terms of discriminant, you are in the realm of quadratic equations. So try to find the quadratic equation, as crazy as it might seem. And in this case, it was staring at us this whole time. And so from this step here, you can go ahead and define little a, little b, and little c. Okay, remember that this comes from ax squared plus bx plus c. And so little a is what's in front of x squared. So in front of my x squared, in this case a, we have a 1 times a. So little a is going to be 1. For this next part, we have minus 3 for b. And for this next part, as crazy as it is, your c is ln k. After all, ln k is just a number. And so from here, you can use the discriminant, right? And so the discriminant, we said, and from the formula booklet we know, it's going to be b squared minus 4ac. So first, let's find out what my discriminant is, and then let's apply this thing here, the greater than or equal to 0, because we're talking about at least one real solution. So first, let's solve for the discriminant. So if you go ahead and plug in, you end up with b squared is negative 3 squared minus 4 times a, which is 1, times c, which is ln k. And so all of this equals your discriminant, okay? So your discriminant ends up being 9, because negative 3 times 3, minus 4 ln k. All right, interesting. And so from here, we need to apply our condition, which is the discriminant being greater than or equal to 0. So this whole thing has to be greater than or equal to 0. And so because we want to find the values of k, try to get k alone. So from here, what I would do, there's a couple different ways, but what I would do is just plus 4 ln k to both sides. That way you get k a little more alone, right? So this goes away with this. You end up with 9 being greater than or equal to 4 ln k. You want to keep getting k alone, so you can divide by 4, divide by 4. You end up with 9 over 4 is greater than or equal to ln k. Now, just because for me it's easier to visualize it, I'm going to flip it for a second. So ln k is less than or equal to 9 over 4. See? And from here, we're pretty much at the last step. And so from here, you need to find the value for k. You already got k alone as much as you can. And the last step is a little bit creative. Okay, you have to be familiar with logs and stuff like that. And so because we need to be familiar with logs, let's go to my formula booklet and look for logs. Oh, it's actually just right there. So as you can see here, first things first, the exponential function and the logarithmic functions are like inverse of each other. See? So for example, in math, you have plus and then you have minus. You also have multiply and then you have divide. Like all of these are opposites, right? And so you also have the exponential function and the logarithmic functions. Okay, those are also opposites. And so how do you like read the logs? Well, this is actually how the exponential function interacts with the logarithmic function. But technically the definition of log, I hope it's here, else I'll just give it to you, but logarithmic, is there really not the definition of log here? Wow, that's crazy. You learn something new every day. Oh, there it is. Okay. So here, sorry about that. This is the definition of log. What I showed earlier, I'm going to leave it in the video because it's still relevant. It's how the exponent function interacts with the logarithmic function. But this is like the hardcore definition of log. See? So notice here. Basically, what's happening, start from this side. Okay? Start from this side. So basically, what you ask your logarithmic function is your base to the power of something gives you what's in parentheses. Your base to the power of something gives you that parentheses. It's the same thing. Okay? And so if I go over here, your base, what is your base here? It's natural log. And natural log always has a base of e. Normal log always has a base of a. I mean, damn, sorry. Normal log has a base of 10, unless they tell you otherwise. Okay? If they tell you otherwise, you have a different base. But the standard, the default, is that natural log has a base of e, log 10 has a base of 10. And so here you're asking, like this whole thing basically, is that e to power of something, something is on the other side, right? It's on the other side. So e to the power of that something, 9 over 4, has to equal k. Ah, okay. So now we're getting somewhere. And so this now gave me like how far k can go. Okay? If k goes anywhere beyond this, it stops working. But anywhere less than this, it's okay. See? How do I know this? Because ln k has to be less than or equal to 9 over 4. And so because it has to be less than 9 over 4, then k can go as far as 9 over 4. All right, awesome. And so for writing down the range, well, ln k in this function here, it's inside a logarithm. And so something that I didn't tell you earlier, but I tell you now, is that the logarithm, the value that's inside, has to be positive. And so whatever's inside has to be positive. And so now, for example, if I pull up a quick graph on Desmos, just so you can see it, here I'm graphing ln of x. Notice how the inside, my x values, I don't have a single negative x value. I have negative y values, yes, but there's not a single negative x value, okay? Because what's inside my parentheses has to be positive. And so that immediately tells me that k, okay, k has to be greater than 0. And I just found out from down here that this is the maximum value that k can take. So k has to be greater than 0, and also it has to be less than or equal to e to the power of 9 over 4. And that, ladies and gentlemen, is how you do number 5. So again, I don't think it's incredibly hard, but the hardest part, for me at least, is realizing you have to use discriminants. Now, I've also realized, because I've done a couple of these tests already, is that the thing, when it says has at least one real solution, it's a massive buzzword. Okay, it's a massive hint that you need to use discriminant. So whenever you read at least one real solution, or at least two real solutions, or even no real solutions, whenever it talks about solutions, bada bim, bada boom, you're talking about discriminants, you're talking about the quadratic function. Try to find the quadratic function. I know it can be hard to visualize, so substituting can be a very good idea. Ladies and gentlemen, that is number 5, and I hope it helped.